Today's topic is closure properties for the regular languages. We should recall that a closure property is a statement about a certain operation on languages that says when the arguments are languages in the class, then so is the result. You can see on the title slide the list of closure properties for the regular languages that we are going to discuss. Our first closure property will be union. That is, if L and M are regular languages, so is L union M. To prove this fact, we use the regular expression, say R and S, whose languages are L and M respectively. We know L and M have regular expressions because they are assumed to be regular languages. Then R plus S is also a regular expression, and we know its language is the union of L and M. The same idea works for concatenation and closure. Remember to draw parentheses around R and S if they are needed, like this. For example, if R is 0 plus 1 and S is 0, then you need to write the expression with parentheses around the 0 plus 1, otherwise you'll get the wrong language. You don't need the parentheses around the 0. Regular languages are also closed under intersection. For intersection, we can't use regular expressions very easily, but the DFA is perfect for proving closure under intersection. So we take DFAs A and B for the two languages whose intersection we want, and we construct the product automaton. The final states in the product are those states that are final in both of the given automata. Thus, the product accepts an input string if and only if both of the original automata do, and that's exactly what we want for intersecting the languages. Here's an example based on the same product automaton we used last time. The only final state in the product is BC. That's this, of course, because B and C are the only final states of their automata. B and C are there. Here's an example of how closure properties prove useful. Okay, remember we proved using the pumping lemma that L1, the set of strings of zeros followed by an equal number of ones, is not a regular language. L2, the set of all strings with an equal number of zeros and ones, isn't regular either. However, suppose L2 were in fact regular. Then since regular languages are closed under intersection, the intersection of L2 with the language of the regular expression 0 star 1 star would also be regular. Now the language of 0 star 1 star is all strings with any number of zeros followed by any number of ones. But what is the intersection of L2 with this language? It is L1, because L2 forces the number of zeros and ones to be equal, while the language of 0 star 1 star forces all the zeros to precede all the ones. Set difference is another operation under which regular languages are closed. The difference of languages L and M, written L minus M, is the set of strings in L that are not in M. For the proof of closure under difference, start with DFAs A and B for languages L and M respectively. Construct C, the product automaton for A and B. Make the final states of C be the pairs where the state from A is final and the state from B is not. Then C accepts an input string W if and only if A accepts W but B does not. That is, W is in the difference of their languages. Here's our favorite product automaton again. This time, BD is the only final state. Because B is the only final state of the orange automaton, and D is the only non-final state of the purple automaton. Notice that the final state BD is not reachable from the start state, so this version of the product automaton accepts the empty language. That's exactly as it should be, because the first automaton, the orange one, accepts a subset of what the second automaton, the purple one, accepts. That is, the first automaton accepts all strings that end in an odd number of ones, while the second accepts all strings that end in at least one one, plus the empty string. The complement of a language is defined with respect to some alphabet sigma. Sigma has to include all the symbols from the alphabet of the language L, but may include other symbols that don't appear in L. then the complement of L is all strings in sigma star that are not in L. Since sigma star is surely a regular language, and we know that regular languages are closed under difference, we immediately know that the complement of any regular language is also regular. Now we shall look at the operation of reversal. Recall one of our earliest examples of a regular language was the language of binary strings that, when interpreted as integers in binary, were divisible by 23. We commented then that the language of such strings that, when reversed, were divisible by 23 was also a regular language. We also said that constructing a DFA for that language is tricky. So here's the tricky construction, which really isn't so tricky now that we have mechanisms like regular expressions to work with. First, the notation we use for reversal is superscript R. That is, L super R means the reversal of language L. This language consists of the reversals of all the strings in L. Here's a simple example. L has three strings, 0, 0, 1, and 1, 0. Then L reversed is the reversal of each of these strings. 0 reversed is still 0, while 0, 1 reversed is 1, 0, and 1, 0, 0 reversed is 0, 0, 1. So L reversed consists of 0, 1, 0, and 0, 0, 1. To begin the proof that regular languages are closed under reversal, we start with a regular expression for a regular language L. We'll show by an induction on the number of operators in the regular expression that there is a regular expression for the reverse of L. The basis is expressions that are either single symbols, the empty string, or the empty set. These are the only expressions with zero occurrences of operators. In all these cases, the expression doesn't change. That is, the reversal of a string of length 1 is the same string. The reversal of the empty string is still the empty string, and if you reverse all strings in the empty set, the set is still empty. The induction consists of the three operators for regular expressions. For union, it is easy. You just reverse the expressions for the two parts of the union. Concatenation is a little trickier. To reverse a string wx, where w comes from f, say, and x comes from g, you need to reverse w and reverse x, but then you need to flip the order of the reverse strings. That is, x reversed comes before w reversed. For example, if w is 0, 1, 1, it's w, and x is 0, 1, then the w reversed is 1, 1, 0, and x reversed is 1, 0, but the x has to come first, so the reverse of 0, 1, 1, 0, 1 is in fact 1, 0, 1, 1, 0. And for the star, we reverse the expression f that is starred. That's this guy here. So it now produces the reverses of all the strings that f produces. We then star the reversed expression to get concatenations of any number of the reverse strings in any order. Let's reverse this regular expression. Its language is all strings of zeros and ones such that the first bit never again appears. That is, the strings are either a 0 followed by any number of ones, that's this part, or a 1 followed by any number of zeros, that's that. The outermost operator of this expression is the plus, and the way we reverse a sum of two expressions is to reverse each expression separately. That is, the reverse of this whole expression is the reverse of the two parts separately. Now let's look at one of the expressions 0, 1 star. We have to, let's look at this. We have to reverse it. So the way we reverse a concatenation is to reverse each of the component expressions and put them in reverse order. So 0, 1 star, its reverse is 1 star reversed followed by 0 reversed. The other expression, 1, 0 star, which must be reversed, is handled the same way. It's 0 star, and we have to reverse that, followed by 1, which we must reverse. Okay. The basis rule tells us the reversal of 0 is 0, and the reversal of 1 is 1. That is, the reversal of this 0 is just that 0, and the reversal of 1, again, is just that 1. Also, the reversal of 1 star is the star of the reversal of 1. That's that. And similarly, the reversal of 0 star is the star of 0 reversed. Finally, the reversal of 1 again, that's this, is just 1. So we get 1 star 0. And the reversal of 0 again is just 0, and we get that. Now we have no reversals left, and we are done. The resulting expression is what you would expect. Its language is the binary strings where the last symbol does not appear elsewhere. Homomorphisms are transformations on symbols that replace each symbol by a string, which may be empty, another symbol, or a long string. When a given homomorphism is applied to all the strings of a regular language, the result is a regular language, as we shall see. Here's an example of a homomorphism, one that we shall use repeatedly in the discussion. This homomorphism H replaces every 0 by the string AB and replaces every 1 by the empty string. We apply any homomorphism to a string by applying the homomorphism to every symbol of the string in order and concatenating the results. For example, if we apply our homomorphism H to the string 0, 1, 0, 1, 0, each of the zeros gets replaced by AB, and the 1s effectively disappear because they are replaced by the empty string. That is, this 0 becomes that AB, this 0 becomes that AB, that 0 becomes that AB, and the 1s are replaced by epsilons that sort of go in the middle there, but you don't see them, of course, because they're empty. Thus, H of 0, 1, 0, 1, 0 is AB, AB, AB. We claim that if you take a regular language L and apply a homomorphism H, then the result is also a regular language. Note that the result of applying H to the language L is the set of strings you get by applying H to all strings in L. I'm not going to give you a formal proof, but the big idea is that you start with a regular expression for L, and you apply H to every symbol in that regular expression. The result will be a regular expression for L. Here's a simple example. H is the homomorphism we have been using as an example right along, and L is also a language whose regular expression E we saw before in connection with reversal. We compute an expression for H of L by replacing each occurrence of 0 in E by AB and each occurrence of 1 by the empty string. The resulting expression is this one. Okay. That is, this 0 got replaced by AB, this 1 got replaced by the empty string, that 1 got replaced by the empty string, and this 0 got replaced by AB. By the way, here is a good example where you have to introduce parentheses, since 0 star needs no parentheses, but AB star, that is, if I wrote just this, would be wrongly interpreted as an A followed by any number of B's. Rather, what we mean is any number of unit ABs. We can simplify this expression considerably. First, epsilon star is any number of empty strings, so we can replace AB epsilon star, that's this, by just AB epsilon. Remember that the empty string is the identity under concatenation. So we can remove the epsilons to give us just AB plus AB star. That is, these guys go away, leaving us just that. Okay. But the language of AB is just one occurrence of AB, while the language of AB star is any number of occurrences of AB, including exactly one occurrence. Thus, we can just drop the term AB here, and we are left with just AB star. That's the simplified expression. We can also define the inverse homomorphism of a language or a string. We denote inverse homomorphisms by a superscript -1. That's this notation here. The result of applying the inverse of a homomorphism H to a language L is the set of strings W, such that when you apply H in the forward direction to W, you get a string in L. So here is the language L. These are all the strings in the language L. Okay, and H will be represented by downward motion. So any string that goes anywhere in L, when you apply H, these are all in H inverse of L. And any string that misses L when you apply H, that's not in H inverse of L. Here's an example. Let H be the homomorphism of our running example. L is the language with two strings, A, B, A, B, and B, A, B, A. Okay. That's that right there. Then H inverse of L is the language of strings that have two zeros and any number of ones interspersed. Here's a regular expression for this language. To see why, let's look at the two strings in L. Okay, A, B, A, B, and B, A, B, A. A string like 1, 1, 0, 1, 1, 0, 1 maps to A, B, A, B. The ones disappear as they go to empty string, and the first zero goes to that AB, the second zero goes to that AB. But nothing can go to BA, BA because a zero, say, has to cover that AB in the middle. That's the only way you can map a zero. Now you've got to be able to map something to the B, but the only way you can do that is if you have a zero, but that would then map to AB. And similarly, this A, there's no way to map to that A without mapping to another B which doesn't exist. While for forward homomorphism, the regular expression representation was dandy, to show that the inverse homomorphism of a regular language is regular is best done with DFAs. Start with a DFA A for L and construct a DFA B for H inverse of L. B has almost everything the same as A, the same states, the same start state, the same final state. But the input alphabet for B is the appropriate input alphabet, that is, the set of symbols to which the homomorphism H applies. We then fix up the transition function for B to reflect both the new set of input symbols and the effect on those symbols of the homomorphism. Suppose B is in state Q, and the input symbol is A. We apply H to A, and we see where the automaton capital A would go on that sequence of inputs H of A. That is, delta B of Q and A is delta A, that is the transition function for the automaton A, starting in state Q, but reading sequence H of A. Note that H of A could be the empty string or some long string of symbols. So this is really the extended delta, but that's okay. We know what that is. Here's an example automaton, and we'll use the same homomorphism we've been playing with all along. Since H of 1 is the empty string, each state of the automaton for the inverse homomorphism will transition to itself on 1. That's what these transitions, for example, are suggesting. For transitions on 0, we need to figure out where the original automaton goes on AB. For example, starting in state A and following the path labeled AB, you wind up in state C. That explains why the transition from A on 0 goes to C. Similarly, starting at B and following the path labeled AB, it's that, you also get to C. And the same thing is true if you start from C, A and then B. We're not going to do the complete proof that regular languages are closed under inverse homomorphism. The heart of the proof is an induction on the length of W that says that W takes automaton B from the start state to state P if and only if the string h of W takes automaton A from the start state to the same state P. That's this equation. Now B accepts W and A accepts h of W if and only if P is a final state. That is, W is in the language of B if and only if h of W is in the language of A, which is the same thing as saying B accepts the h inverse of the language of A.